We're continuing our study of probability for finite mathematics students, and in this video we will consider conditional probability, probability of an intersection, and what it means for events to be independent. To start with, conditional probability is read the probability of A given B. And what that means is the probability that event A occurs if you already know that B has occurred. And we can calculate that conditional probability with the formula. The probability of A given B is equal to the probability of A and B happening simultaneously divided by the probability of B. And for the product rule, when we have the probability of A and B, that is going to be equal to the probability of A times the probability of B given that A has already occurred, or the probability of B times the probability of A given that B has already occurred. Now, when the two events are independent, that means that the results or the probability of A has no connection to the probability of B. They don't affect one another. If the two events are independent, then what we can say is that the probability of their intersection, remember that the intersection means and, so the probability of event A happening and B also happens, is the product of their two probabilities. But that product formula only works when the two events are independent, or in other words, what happens in A doesn't affect B. For example, an example of two independent events. If I have two dice, one red, one green, and I drop the two dice at the same time, I roll the two dice at the same time, the probability of getting whatever on the red dice has no effect on how the green dice falls. So those are examples of independent. Here's an example of two events that are not independent. And I have a short video, by the way, that gives a mnemonic on how to remember this. So you might you might want to jump to that video at some point also if the idea of independence is blurry to you at all. But for independence, two events that are not independent of one another. Let's say that you have this glass jar or glass bowl with some marbles, and it looks like we've got 3 red marbles and 2 blue marbles, and you reach in to take a marble out and you get that blue one. When you reach back in, the probability of getting blue is now 1 in 4. Now, when that blue marble was there, it was 2 in 5, right? But when we remove 1, it comes out, then the probability of getting that second blue marble changes. That makes it independent. Here's what we would refer to this as is with or without replacement. So if we don't replace the blue marble, or the problem might be stated without replacement, that simply means we don't put that marble back in before we take our second draw. Then notice that the probability changes. Now, on the other hand, if I were to do this problem and I draw 1 marble and the probability of getting that blue marble is 2 out of 5, and then I put that blue marble back, the probability the second time I draw is still 2 out of 5. That's with replacement. But whenever we're talking about an example without replacement, then the two events are not independent. Well, let's jump into some of those examples. Here's our first example. Given the probabilities in the table, for events in a sample space S, find the probabilities relative to the probabilities in the table. Some of these I just pulled right out of the table. We can see that the probability of C is 36 hundredths, just right off of the table, right? The probability of F is 80%. The probability of A and F happening together, so where column A and row F come together, is 5/100ths. And then C and E, so where C and E come together, is 6/100ths. So there's some of the probability we can do just pulling the values off of the chart. Let's use these values now to look at some conditional probability. What's the and that's this number 5 is where we'll start. What's the probability that event A occurs given that the event F has already occurred? We're going to use this formula, the probability of A and F both occurring, divided by the probability of F. So that's 5/100ths divided by 8/10ths, or 80/100ths, and that gives us a probability of 6.25%, or as a decimal, 0.0625. Number 6, the probability of F and A occurring together was the 0.05. And then the probability of A occurring is 0.07. And when I divide those, I get approximately 71.4%, so 0.714. Probability of D, given that E has already occurred, we're going to do the probability of D and E. Could I encourage you, by the way, to write this formula each time? If you'll write that each time, there's not that many examples here, but if you'll write that each time, then by the time you finish this section, the notes and then the homework, you're going to have a much better likelihood of remembering the formula and remembering how to apply it. But the probability of D and E occurring simultaneously, that looks like a 0.04. And then we divide that by the probability of E, which is 0.2. And when those divide, we'll get 20%, so 0.2 or 20%. And then number 8, the probability of E, given that B has already occurred, probability of E and B both occurring is 8/100ths. And the probability of B occurring is 18/100ths. And when we divide those, we get approximately 44.4%, 0.444. And then this is an interesting one. What's the probability of C, given that C has already occurred? Well, that's just going to be a 1, right? But let's work out the formula just so you can see it. What's the probability of C happening and C happening? The probability of C and C is going to be 0.36. And the probability of C is 0.36. So of course it happens once, right? The probability is 100%. If we already know that the event has occurred, then what's the probability that the event occurs? It's 100% because we already know that it occurred. Let's continue with number 10 and 11. Are events C and E independent? Why or why not? If they are independent, then the probability of C and E will equal the probability of C times the probability of E. I can pull these examples from the chart and from the previous example that was worked, but the probability of C and E occurring at the same time, that's going to be 0.06. If I multiplied the probability of C times the probability of E, the probability of C is 0.36, and the probability of E, 0.2. And when I multiply those, I get close, but not precisely, 0.072. And so the probability of C and E, 0.06, does not equal the probability of C times the probability of E. So we can see that they're not independent events because the product rule didn't work out. Let's try one more example of this. Are B and F independent? Why or why not? What's the probability of B and F? I can see that the probability of B and F is 10 hundredths, or 0.1. So that's where B and F intersected, right? 0.1. And then the probability of B occurring added up to 0.18. Probability of F, 0.8. When I multiply those, I get 0.144, which is not equal to 0.10 or 0.1. 10% and 14.4% are not equivalent. So the events if the events are independent, then the outcome of the first won't affect the outcome of the second. But in this case, that's not happening. What happens with event A does affect event B. Or, I'm sorry, event B does affect event F. So since the outcome of the first could affect the outcome of the second, the events are not independent, and by definition, the probability of B and F is not equivalent to the probability of B times the probability of F. So that's independence in this important definition with the formula for how we determine if they're independent or not. Moving on to a problem that we'll describe as being with or without replacement. On this first example, number 12A, the ball is replaced, right? We pull out a ball and then we put it back. In the second example, we're going to do the same problems but without replacing that ball, and we'll see how the outcome changes. So if we wanted to see if the first ball is drawn and then replaced, what's the probability that we get a green? 7 out of 20. We put that green ball back, and so what happened the first draw doesn't affect what happens with the second draw. So we could use this formula that it's 7 over 20 divided by 7 over 20. So that gives us 49 over 400, or 12.25%. And now how about the first time we draw, it's not green. So that looks like it would be 13 of the balls are not green. We put that non-green back and draw out another time, and our probability the second time is a 13 again. So it looks like we get 169 out of 400, or roughly 42.25%. 0.4225, and then we can change it to a percent. How about the probability that at least one is green? What's the probability that at least one of the two balls is green? Well, if I have already calculated what's the probability that there's no green, I could use the complement formula, 1 minus the probability of no green. Neither ball is green. That's the 0.4225, right? So I could do 1 minus 0.4225, which gives me 57.75%, or 0.5775 as a decimal. Now this part 4 is going to be a little trickier. What's the probability that the two balls are not the same? The probability that the two balls are not the same, we've got to say the probability of red and not red. And then add that to the probability of green times the probability of not green. And then add that to the probability of white times the probability of not white. Do you follow that? The two balls are not the same color. That means we get a red. If the first one is red, then we get green or white. And then if the first one is green, the second one's got to be red or white. If the first one was white, then the next one has to be red or green. But each time we're putting that ball back before we draw the second. So we've got the probability of red times not red is 5 over 20 times 15 over 20 is 75 400ths. Green times not green, 7 over 20, 13 over 20 gives us 91. Probability of white and the not white, 8 over 20 and 12 over 20 multiplied gives us 96 out of 400. And when I add those up, I'm going to get 262 as the numerator, and then the denominator stays the same. Feel free to use your scientific calculator to do those fractions if you're struggling with that at all. But when I divide this, I get 65.5% or 0.655. Can we try the same example if we don't replace the first ball? So watch how it changes slightly. What's the probability that they're both green if I don't replace it? So the first one, there's 7 greens, and then out of 20. And then if I don't put that green one back, we have 6 greens left, and there's a total of 19 left. So you could multiply those to finish that up. Neither ball is green, so the probability that the first one is not green, there's 8 plus 5 that are not green. And then if I get one that wasn't green and put that, keep that out, now there's 12 that are not green out of 19. And I'll leave that one for you to multiply also. Neither ball is green, 13 out of 20 times 12 over 19. Probability that at least one is green. We're going to do the 1 minus the probability that there's no green. The answer we got for double I right here, right? And then the two balls are not the same. What's the probability that the two balls are not the same? So we'll have the probability of red, 5 over 20, times the probability of not red, 15 over 19. Add that to the probability of green times not green. Add that to the probability of white times not white. So we'll add that to 7/20ths times 13/19, and add that to 8/20ths times 12/19. Notice that by nature of this problem, I'm going to get a common denominator already, and when I add those products, I'll get 262 out of the 280. It could be reduced, so make sure you reduce that also, but the percent is 68.9%. I'm going to stop the video here And if you'd like to see more examples, I'll continue in a part 2 of this video. But the guided notes come from the Pearson workbook, and that's where these examples are coming from. If you're confident and comfortable continuing those examples on your own, you could do so without the use of the video, but feel free to use this next video coming up if that's an easier way for you to complete those notes.